Now, hydrolysis of acetals and ketals, this is a reversible reaction, and it is opposite to the acetal and ketal formation. So this is going to be the reverse of the reaction that we introduced earlier, where we formed the ketals and the acetals in there. And in this reaction, normally you start with either an acetal or you start with a ketal. Okay? If this one is an acetal, then it needs to have a hydrogen here. If it's a ketal, then there are two R's in there. But the ORs are a must for the acetal and the ketal. And you do hydrolysis. Hydrolysis is simply adding water in presence of any acidic medium like H2SO4, but we represent the acid as H+. This means that this is an acid, just any strong acid in the solution. And in this type of reaction, what you are doing, since you're doing hydrolysis, you are breaking the CO bond. So you're breaking those two COR bonds. These are the bonds of the acetals and the ketals. You're breaking them and you're returning the structure back to its original, which is the carbon double bond. Okay, so that carbon in here is going to have both sigma bonds broken, and you're going to form a pi bond. The oxygen comes from the water addition, but you're not responsible to know the process of how did we obtain this, but you're responsible to just draw your product in there. So let's go ahead and have an example. Before that, you will have, of course, your byproduct in there. Whenever you break and you form your carbonyl, your byproduct is going to be the two ORs that you're forming. This is back to the alcohol in there. So that is going to be two alcohols. And this is because the alcohol was in excess. Remember in the reaction before, we used excess alcohols, we reacted with the carbonyl to form the acetal or the ketal. This is its reverse. You form the acetal and ketal, you add some water together with the acid, and you're back to the carbonyl again. So let's go ahead and have an example. Let's say, for example, if I have this acetal here. This is the OCH3, and I am reacting it with water in presence of an acid. So immediately this is what you need to do. Locate the carbon that has the two ORs. And then you are going to break this bond and break this bond and change that carbon into a C double bond. We are not adding carbons. It's still here. So all what you need to do is just add a double bond and an oxygen there. Okay, whether you represent it like this or you represent it like this, guys, it is the same. So these two are the same representation of the same ketone structure that has 3 carbons. So this is going to be a propanone. It's exactly the same. Plus, of course, my byproduct in there, the alcohol that I broke. I have a CH3O and the CH3O. Just add a hydrogen on each one of these oxygens there. And your product is going to be a CH3OH, and it's 2 of them. Okay, and that is going to be your excess alcohol byproduct that you are going to form. Remember, an alcohol is an ROH. So you need to keep it an ROH. So all what you're doing here is you're adding a hydrogen here and the hydrogen there. Just put a note that you are adding a hydrogen here. So we're going to add a hydrogen here. We're going to add a hydrogen there to create back our alcohol. Same idea. Here again, I'm starting with a ketal in there. So it really matters if you're starting with a ketal or if you're starting with an acetal. I know I'm starting with a ketal because there is no hydrogen here. So I know that my carbonyl is going to be a ketone. Okay, this is a ketone carbonyl. Same thing over here. I am starting with a keto. So my carbonyl is going to be a ketone. So I'm going to break this bond, break this sigma bond in there, and change the carbon of the cycle. I'm not adding any additional carbon. So this carbon is going to turn into a double bond O. So I'm just going to add the double bond O in there. And then see what I have here. I have two different types of alcohols. I have a CH3O. I'm just going to add a hydrogen here, and I'm going to add a hydrogen there to the CH2CH3O, so that I can make my different alcohols. Now, I cannot group those alcohols because they are different, so I need to show them separate. Plus a CH3, CH2, and an OH. Notice how did I write it down? I didn't write it down as a CH2, CH3. It's very important. Connectivity is very important. You always start with a CH3. So these are the two alcohols that I am forming in this case. And the reason why, because my ketal that I had did not have the same ORs. So if it didn't have the same ORs, I cannot group them together. I need to show them separate as two separate alcohol molecules in there. Now for the acetal, I know it's an acetal because I do have a hydrogen here. Okay, so all what you need to do is just highlight the carbon in there and then break the two OR bonds and turn the carbon into a carbonyl. Add your or number your carbons, or make sure that you add your carbons in there and don't add any additional carbon. Okay, so I do have 1, 2, 3, 4, 5, 1, 2, 3, 4, and 5. So this carbon now is going to be my carbonyl in there. I still have my hydrogen to be my aldehyde. So I know here that I am forming my aldehyde. The two ORs are the same, so I'm just going to go ahead and group them together instead of the R. This is not a general example, it's a specific one because I know what the R is. It's a CH3, so that is going to be a CH3OH, and I have two molecules of that, and this is my excess alcohol. This reaction is called hydrolysis of acetals and ketals, where you go back to your aldehyde or ketone, depending on the acetal and the ketal that you start with. Now, there are multiple tests in the lab that we do to identify aldehydes and ketones. The first one is oxidation. And normally when you do these lab tests, the type of identification is by color. So if the color changes whenever you mix compounds together, if the color changes, this means that there's a reaction. If it did not, then this means that there is no reaction. So in oxidation, normally the solution of the sodium chromate is orange. And I know that this is an oxidizing reagent that turns this hydrogen into an OH. So this is a simple test I can do to aldehydes, where the hydrogen of the aldehyde simply turns into an OH in there, and the color of the solution of the carboxylic acid is going to change from what it starts. The aldehyde is always colorless, and when you do the oxidation, the aldehyde will change into a carboxylic acid, which is a green color. So this is why we say this is a positive test. A positive test is a test where the reaction happens, okay? And the reaction can happen due to color change. If you see a color change, then this means that the reaction here happens in there, and you go from one color to the other. So here I'm going from a colorless to a green color solution. A normally short chain carboxylic acid have a green color in there. Once you mix the sodium chromate, which is orange, with the colorless solution of the aldehyde and shake, the orange color does not stay the same. The orange color turns into a green color, which is again a positive identification that the hydrogen of the aldehyde was oxidized into an OH. Okay? Now with ketones, if I use the same thing, if I use the sodium dichromate, which is orange, and I mix the solution together, the color will remain orange. So there will be no reaction in there because the color of the solution remains orange. Okay, I'm starting with a colorless ketone, mixing it with orange. So the solution here is orange. And if I keep mixing, it doesn't change. It stays orange, so I know that there is no reaction with oxidation. This is one way to identify aldehydes from ketones. Aldehyde have a reaction with oxidation. Ketones, they don't have a reaction with oxidation. Another test in order to identify aldehydes from ketones is Benedict oxidation reaction. It's the same idea in here. It's still an oxidation reaction, but the reagent is going to differ in this case. And I am using here copper ions in presence of a basic medium. I represent it like this, okay? That Benedict solution will oxidize the hydrogen of the aldehyde into a carboxylic acid. So this hydrogen here is going to turn into a carboxylic acid, and it only works on the hydrogen of the aldehyde. Now, on its way during the oxidation with the aldehyde, you will form a red precipitate. When the copper reacts with the water, it will form a red precipitate, and that red precipitate is a CuO. This one is going to be a red precipitate. And that red precipitate you're going to see as a form of a solid at the bottom of the test tube. This is an identification that the reaction happened in there, okay? So aldehydes can easily get oxidized with Benedict solution, and the hydrogen of the aldehyde turns into an OH, and you're going to see a red precipitate. So this is a must to write in this reaction, because this is what shows that the test is positive, okay? This means that the aldehyde was simply oxidized. Ketones, they will show no reaction with the Benedict solution because there is no additional hydrogen on the carbonyl to get oxidized. So you will see no reaction. You will see no red precipitate. The third reaction that also we use in the lab to identify aldehydes from ketones in there is the Tollens test. And the Tollens test is used to identify aldehydes only, not ketones. Ketones have no reaction. So far, guys, the oxidation test identifies aldehydes, the Benedict test identifies aldehydes, and the Tollens test. The Tollens test is a combination of a reagent, which is made up of silver, ammonia, and a hydroxide. So the silver, the ammonia, and the OH is the basic medium in there. You combine everything together, and that is called the Tollens reagent, okay? You are responsible to know it's a structure in there, or instead of writing it down like this, I would write Tollens reagent, okay? Now, what is happening here? I'm again oxidizing this hydrogen in there. But because the medium here is a base, I cannot get the acid. I need to get the base of the acid. So all what you need to do for this reaction is replace this hydrogen with the oxygen. That's it. Okay? So we're going to get the base of the acid. So we're going to replace the hydrogen with the oxygen. Now, if I do this, now we know that this oxygen is going to be a negative charge. Why? Because we know for formal charges, when oxygen has 3 lone pairs and a single bond, it will be a negative charge. And then, of course, that needs to be balanced with a positive charge. And your positive charge ion is going to be an H4. We will produce an H4 when ammonia simply over here reacts with the water, because we do have water here. So you're going to end up having your NH4 counter ion that balances the negative charge, and that is going to be called the base of the acid. So instead of forming an OH here, I can't, because the medium is a basic medium. So the acid will not hold, so I will form a base in the basic medium. That will be more stable in there. So that is going to be the base of the acid. And that is going to be a positive test in there. Plus, what I am going to form is a silver solid precipitate. So that silver, it's going to be look like a precipitate on the walls of the test tube, and it's going to be kind of like a mirror. You're going to see a very shiny silver color on the walls of the test tube, and this is an indication that the reaction here is positive, meaning that the reaction happens. Okay, this is another example. So all what you need to do is just highlight this hydrogen, turn it into an oxygen, and balance it with the NH4. So, and don't forget your charges. This is a carbon double bond O. So turn the hydrogen into an oxygen, put a negative charge, and balance it with an H4 in there. And please don't forget that you are forming the silver precipitate. When I say precipitate, meaning that it is a solid, and that solid will precipitate along the walls of the test tube and makes the test tube kind of like shiny, like a mirror in there, so that you will know that the reaction happens. This Ketals test is called a silver mirror test as well. So we call this a silver mirror test.